What James Webb saw beyond the stars is a story that begins where our understanding of time used to end. For decades we believed there was a wall, a point in the cosmic past where the very first light began to flicker and before which there was only darkness. But as the James Webb Space Telescope turned its golden mirrors toward the deepest voids of the sky, it found something that should not be there. To understand why this matters, we have to go back to a time before Webb ever existed. A time when the most powerful eye in the sky belonged to a different telescope, one that had already changed everything we thought we knew about the universe. Its name was Hubble, and for more than 30 years, it was the instrument that defined the edge of the visible cosmos. Hubble showed us galaxies we never knew existed. It revealed clusters of stars stretching back billions of years. It gave us that famous image, the Hubble Deep Field, where a tiny patch of sky, no bigger than a grain of sand, held thousands of galaxies within it. That one image changed the way humanity thought about space, because suddenly we realized the universe was not just big, it was unimaginably full. But Hubble had limits. It could only see so far. It could only peer so deep into the past before the light itself became too faint, too stretched, too ancient to be captured by its mirrors. And at a certain point, when Hubble looked into the deepest dark it could reach, it simply stopped seeing. The galaxies thinned out. The light faded. And beyond that, there was nothing. A wall. A curtain drawn across the earliest chapter of the universe. Astronomers gave this region a name. They called it the Cosmic Dark Ages. It was the period after the Big Bang when the universe was still cooling, still finding its shape, still waiting for the first stars to ignite. No one had ever seen into it, not directly, not with their own eyes or with any instrument humanity had ever built. The Dark Ages were a mystery sealed behind time itself. And then James Webb launched. On Christmas Day of 2021, a rocket carrying the most complex scientific machine ever built lifted off from a jungle in South America. Inside that rocket was a telescope the size of a tennis court, folded up, like cosmic origami, waiting to unfold in the silence of space. The journey took a month. The unfolding took another month. And when it was finally done, when the golden hexagonal mirrors had locked into place 1 million miles from Earth, something remarkable happened. Webb opened its eye. And for the first time in history, humanity had a telescope that could see through the wall Hubble had hit. Webb was not just more powerful than Hubble. It was a completely different kind of instrument. Where Hubble saw visible light, Webb sees infrared. And that difference matters more than you might think. Because the universe is expanding. And as it expands, the light from ancient objects gets stretched. Visible light over billions of years turns into infrared light. So when Webb looks at something very old, very far away, it is seeing something Hubble physically could not. It is seeing the leftover glow of the first moments, the faint whispers of the earlier stars, the flickering embers of a cosmos that was just beginning to wake up. The first images came back in the summer of 2022, and even the scientists were not ready for what they saw. Because when Webb looked into the void, into the place where Hubble had seen nothing, it did not find emptiness. It found galaxies. Not a few, not a handful, many. Bright clustered ancient galaxies sitting in a region of time that was supposed to be dark. And these galaxies were not dim little smudges. They were shaped. They had structure. Some of them even had disks and spiral arms, the kind of features that are supposed to take billions of years to form. But these galaxies were only a few 100 million years old. By every rule, we thought we understood they should not have looked the way they looked. The early reports were careful. Scientists are always careful with new data. They double-checked the measurements. They ran the numbers again. They asked themselves if something was wrong with the telescope, or with the calibration, or with the way distances were being calculated. But every time they ran the test, the answer came back the same. These galaxies were real. They were ancient, and they were far, far bigger than anyone had predicted. That was the first clue that something strange was happening, that the early universe was not the quiet, slow nursery we had pictured. It was active, it was productive, it was doing things we did not yet understand. And then came the little red dots. That is what the astronomers called them, because that is what they looked like. Tiny specks of red light scattered across Webb's infrared images, showing up in survey after survey. At first, no one was sure what they were. They were too small to be normal galaxies. They were too red to be ordinary stars. They were too distant to be anything local. They were just these strange little crimson points sprinkled across the deep field like cosmic pinpricks. Two of the biggest Webb surveys, called CEERS and JADES, started to catalogue them. CEERS stands for Cosmic Evolution Early Release Science. JADES stands for JWST Advanced Deep Extragalactic Survey. These are long names for what are essentially two massive deep dives into the earliest reaches of the observable universe. And in both surveys, the little red dots kept appearing. Dozens of them, then hundreds. A strange new population of objects that no one had predicted. And the more astronomers studied them, the stranger they got. Because these red dots were not just old, they were massive. The calculations suggested that each one contained the mass of hundreds of millions, sometimes billions of suns. That is a galaxy-scale amount of material. But they were compact, far more compact than any normal galaxy should be. And they were forming when the universe was less than 600 million years old. In some cases, they were forming when the universe was only 300 million years old. That is the cosmic equivalent of finding a fully grown oak tree in a field that was supposed to have just sprouted its first seeds. How do you build that much mass that quickly in a universe that young? No one knows. And that is the mystery at the heart of what Webb has found. Some astronomers began to wonder if the problem was not with the universe, but with our understanding of how galaxies form. Maybe the early cosmos was capable of creating massive objects far faster than we thought. Maybe gas collapsed more efficiently. Maybe stars ignited in greater numbers. Maybe the universe simply had a head start we never knew about. But even those explanations had trouble accounting for everything Webb was showing us. Because it was not just one or two unusual objects. It was a whole category. A whole population of compact, massive, ancient things that should not fit into the standard model of cosmic history. And then came the second theory, the stranger one. The one that made even veteran astronomers raise their eyebrows. What if the little red dots were not galaxies at all? What if they were single enormous stars powered not by fusion, but by something else entirely? This is where the concept of a dark star enters the picture. And once you understand what a dark star might be, it becomes very difficult to look at those little red specks the same way again. The idea is this: in the very first moments after the Big Bang, the universe was filled with two things: ordinary matter, which is what we and the stars and the planets are made of, and dark matter, which is something else. Dark matter is invisible. It does not interact with light. It does not emit radiation. It does not glow or burn or shine. But it has gravity, and there is a lot of it. Roughly 5 times as much dark matter as ordinary matter exists in the universe. And in the earliest moments before the first real stars ignited, dark matter was everywhere. It pooled, it clumped. It gathered under its own gravitational pull. Now here is the strange part. Dark matter does not just sit still. Under certain conditions, dark matter particles can collide and annihilate each other, releasing energy as they do. And if that happens inside a large enough cloud of ordinary gas, something remarkable can occur. The heat from the annihilations can hold the cloud up against its own gravity. Instead of collapsing into a normal star that fuses hydrogen, the cloud becomes a puffed-up glowing giant powered by dark matter itself. That is a dark star, and the theory is that dark stars could grow to enormous sizes. Not just the size of our sun, not just the size of a big star. We are talking about objects that could reach the mass of 1 million suns. Some simulations suggest they could grow even bigger, and they would glow softly, slowly over hundreds of thousands of years. They would not look like stars. They would not look like galaxies. They would look like small, compact, reddish points of light, concentrated in the earliest era of the universe, which is exactly what the little red dots look like. Now, it is important to say this clearly. The dark star hypothesis is not proven. It is one possible explanation among several. But when a team of scientists ran the Webb data through their models, they found that at least 3 of the red dots matched the predicted properties of dark stars almost perfectly. Not just loosely, precisely. The spectra, the brightness, the size, the temperature, all of it lined up. And that is worth sitting with for a moment. Because if even one of those little red dots turns out to be a dark star, it would be the first time in history that humanity has directly observed dark matter doing something. Not inferring it from gravity, not measuring its effect on galaxy rotation, actually seeing its fingerprint in light. It would change everything. But even if the dark star theory does not turn out to be correct, the mystery of the red dots remains, because the universe still has to explain how they got so big, so fast, and so dense in an era when there was barely enough time for anything to form at all. And the strangeness does not stop there, because while astronomers were still puzzling over the red dots, another Webb discovery began to surface. Something that in its own way was just as unsettling. The early universe, it turned out, was full of black holes. And not just any black holes, enormous ones, supermassive ones, the kind of black holes that sit at the centers of galaxies and weigh millions, sometimes billions of times more than the Sun. These objects were supposed to take a long time to grow. You start with a small black hole formed from a collapsing star. Then it feeds. It pulls in gas. It swallows other black holes. It grows slowly over cosmic ages. By the time the universe is a few billion years old, you might have something truly massive at the heart of a galaxy. But Webb was finding supermassive black holes when the universe was only a few 100 million years old. How do you grow a black hole that big that fast? That question has haunted astronomers for years. Even before Webb, there were hints that early black holes were too large for their age. But with Webb's ability to look further and more clearly, the scale of the problem became impossible to ignore. Black holes millions of times the mass of the Sun were appearing in an era when they should have still been infants. Something was feeding them faster than any known process could account for. And that is when Webb caught them in the act. In one survey, scientists spotted a supermassive black hole in the early universe that appeared to be consuming matter at an astonishing rate. The calculations suggested it was swallowing the equivalent of an entire sun every few years. That might not sound fast, but in cosmic terms, it is extraordinary. A feeding frenzy of that intensity sustained over a long period could explain how these early giants grew so massive so quickly. It would require them to be eating at rates that push right up against the theoretical limits of what is physically possible. Astronomers call this the Eddington limit. It is a kind of cosmic speed bump for black holes. If a black hole tries to feed too fast, the radiation from the infalling matter pushes the rest of the gas away. The black hole chokes on its own meal. The feeding slows. In theory, a black hole cannot grow much faster than this limit allows. And yet, Webb is showing us black holes that must have been growing faster than the limit seems to permit. Which means either the limit is wrong or something else is happening that we do not understand. One idea is that these black holes did not start as tiny stellar remnants. They started as what astronomers call direct collapse objects. Enormous clouds of gas that under specific conditions collapse directly into a black hole of tens of thousands of solar masses without ever becoming a star at all. These sea black holes would have had a massive head start, and if you put them in an environment dense with gas, they could grow into supermassive giants in a fraction of the time it would take a stellar remnant to do the same. Another idea is that the early universe was simply denser and more chaotic than we imagined. Gas was thicker, collisions were more frequent, mergers happened constantly. A young black hole could have been surrounded by a buffet of material pulling in more than should be possible because the supply was endless. The feeding frenzy was not a one-time event. It was the entire environment in which these black holes were born. And then there is the third possibility, which is the one that keeps some astronomers up at night. What if we are wrong about the timeline? What if the universe is older than we think? Or what if the processes that govern black hole growth are fundamentally different from what our models predict? We have built our understanding of cosmic history on a particular set of assumptions: the speed of expansion, the age of the first galaxies, the rate at which structure forms. If Webb is showing us things that do not fit, it might not be the universe that is strange. It might be our story about the universe that is incomplete. This is the deeper puzzle Webb has placed in front of us. Not just one anomaly, but a pattern of anomalies. Red dots that should not be so massive. Black holes that should not be so big. Galaxies that should not be so mature. Everywhere we look in the deep field, the early universe is showing us a face we were not expecting. And now we come to another piece of the puzzle, one that sits quietly at the edge of all these discoveries, but which may be the most telling of all. It has to do with the chemistry of the cosmos. Because hidden inside the light of these ancient galaxies is a message written in the iron elements themselves. When Webb captures the spectrum of a distant galaxy, it is not just seeing a color. It is reading a fingerprint. The precise shades and dips in that light tell astronomers exactly what the galaxy is made of. Hydrogen, helium, carbon, oxygen, iron. Every element leaves its own signature in the light. And in the earliest galaxies, Webb has been finding something peculiar. There is too much iron, too much oxygen, too many heavy elements. In the textbook version of the universe, heavy elements are forged inside stars. Hydrogen and helium were created in the Big Bang itself. But anything more complex than that had to be built. Stars take hydrogen and fuse it into helium, then helium into carbon, then carbon into oxygen, then oxygen and silicon into iron. Each step requires enormous temperatures, enormous pressures, and enormous amounts of time. When a massive star dies in a supernova, it spreads those newly forged elements across space. The next generation of stars is born from that enriched gas. Over billions of years, the universe slowly gets more chemically complex. That is the standard story. But Webb is finding early galaxies that already contain significant amounts of these heavy elements. Galaxies that by the usual timeline should be made almost entirely of hydrogen and helium. Instead, they are showing chemistry that implies generations of stars have already lived and died inside them. Generations that we have not yet seen. This brings us to what some scientists are calling the chemical ghost, the traces of a missing generation of stars. A hidden cohort of the earlier stellar objects, sometimes called population 3 stars, that would have lived briefly burned intensely and exploded catastrophically, leaving behind the heavier elements we now detect in their descendants. We have never directly observed a population 3 star. They are theoretical. They are invisible ancestors. But Webb is catching whispers of them in the chemistry of the galaxies that followed. And here is what makes it so remarkable. If Webb is seeing chemical enrichment this early, those first stars had to have formed even earlier than we thought. They had to have been massive. They had to have burned fast and died fast, and there had to have been a lot of them. The idea that the first stellar generation was sparse and scattered is now being challenged. The chemical ghost suggests a much more active, much more productive early universe than any model predicted, which leads us back inevitably to the question we have been circling this entire time. If the early universe was this active, this productive, this mature so quickly, what does that say about the Big Bang itself? What does it say about our timeline, about our understanding of how everything began? Some astronomers have begun to wonder whether we have the age of the universe right. The official figure, based on measurements of the cosmic microwave background and the expansion rate, places the universe at around 13.8 billion years old. But a growing number of researchers have pointed out that the discoveries Webb is making stretch the limits of that timeline. It is not necessarily that the universe is older. It is that some of the structures Webb is seeing should not be able to exist in the time allotted. One possibility is that the universe simply forms structure more efficiently than we thought. That could be due to conditions in the early cosmos that we have not properly modeled. Another possibility is that dark matter plays a more active role in early structure formation than standard models account for. If dark matter clumped faster, pulled in gas faster, and helped build the first galaxies faster, then everything we are seeing could fit within the existing age of the universe. It would just mean that the machinery of cosmic evolution was running at a speed we did not expect. But there are also more radical possibilities. Some theorists have started to revisit the idea that the age of the universe might be off. Not by a small amount, not by a percentage, but in a way that would require new physics to explain. If the universe is older than 13.8 billion years, or if time itself behaved differently in the earliest moments, then the anomalies Webb is showing us might not be anomalies at all. They might be the expected outcome of a universe we simply do not yet understand. This is not a crisis in cosmology, not yet. Scientists are careful about that word. A crisis would mean that the standard model is broken. We are not there. We are somewhere else. We are in the phase where the data is outpacing the theory, where Webb is showing us things faster than the models can keep up. And that is a very exciting place to be, because it usually means a breakthrough is coming. But before we get ahead of ourselves, let us pause and return to those little red dots, because the story has continued to evolve, even since the first surveys. And the more Webb has looked, the more varied they have become. In some images, the red dots are isolated, floating alone against the cosmic background like solitary lanterns in a dark ocean. In others, they appear in small groups clustered together, as if they are gravitationally bound, or perhaps orbiting something invisible. And in a few cases, astronomers have caught the red dots in the process of what looks like merging. 2 or 3 of them drifting toward each other, their soft red halos beginning to blend. If that is what it looks like, then it raises a new question entirely. What happens when two dark stars merge, or two early compact galaxies, whichever they turn out to be? Do they form something larger? Do they collapse into black holes? Do they become the seeds of the massive structures we see later on? We do not know. Webb is still gathering data. Every new field it surveys brings back new information, and some of it confirms earlier theories, while some of it complicates them. But the direction of the research is clear. Scientists now accept that the early universe was doing something different, something more complex, something that our models built on decades of Hubble data and theoretical assumptions did not fully capture. To understand how significant this is, it helps to remember what we thought the early universe looked like before Webb. In the standard picture, the first few 100 million years were a slow, quiet period. The universe cooled, hydrogen atoms formed, gravity began to pull gas into denser regions. Over time, those regions grew thick enough and cold enough for the first stars to ignite. Those stars were massive, hot, and short-lived, and when they exploded, they spread heavier elements into the surrounding gas. The next generation of stars formed from that enriched material. Galaxies slowly began to take shape. Eventually, clusters of galaxies formed. Structure grew, and the universe we see today gradually emerged from that long, patient process. That picture is not wrong. It is still the backbone of modern cosmology. But Webb is adding texture to it. Webb is showing us that the early universe was not patient at all. It was frantic. It was inventive. It was building things faster, earlier, and in stranger ways than we anticipated. And the little red dots might be the most visible symbol of that strangeness. Because whether they are dark stars or compact early galaxies or something else entirely, they represent a category of object we did not know existed before Webb opened its eye. And that is the heart of real discovery. Not just finding more of what you already knew, but finding what you did not know to look for. There is another aspect of all this that often gets overlooked but which deserves attention. And that is how Webb makes these observations in the first place. The telescope itself is a marvel of engineering. 1 million miles from Earth, it floats in a gravitational balance point known as Lagrange point 2, where the pull of the Sun and the pull of the Earth cancel out just enough to let it hold a stable orbit. It is far too far for astronauts to reach. If something breaks, there is no fix. It is utterly alone out there doing its work in silence. And the work itself is astonishing. Webb has a massive sun shield 5 layers thick, designed to block every stray ray of heat from the Sun, the Earth, and even the Moon. Because infrared light is essentially heat. And to see the faint infrared glow of ancient galaxies, Webb needs to be cold. Extremely cold. The telescope operates at temperatures below -220 degrees Celsius. It is one of the coldest places in the solar system. And that cold allows its instruments to detect wavelengths of light that would be drowned out by the telescope's own thermal noise if it were any warmer. The mirror, which is actually 18 smaller mirrors arranged in a hexagonal pattern, is coated in gold. Gold reflects infrared light better than silver or aluminum. Each mirror segment is precisely aligned to a fraction of a wavelength, so that when they all work together, they act as a single enormous lens. If you stood on the Moon and held up a penny, Webb would be able to see both sides of it from its orbit around the Sun. That is the level of precision we are talking about. And yet, even with all this engineering, even with all this investment and care and brilliance, Webb is still surprising us, still showing us things we did not predict, still revealing parts of the universe that were hidden just behind the edge of our vision. Every discovery it makes is a reminder that the cosmos is always bigger, older, stranger, and more beautiful than we thought. Now let us talk about one of the other surprises, something Webb has uncovered that may be even more philosophically unsettling than the red dots or the early black holes. It has to do with galaxy shapes. In the standard picture of galactic evolution, galaxies start out as irregular, chaotic blobs. Over billions of years, they settle into the beautiful spirals and graceful ellipses we see in the modern universe. The Milky Way, for example, is a spiral galaxy. It has distinct arms, a central bar, and a quiet, rotating disk of stars. It took a long time to develop that shape. Most of its evolution happened over the last 8 or 9 billion years. In theory, early galaxies should look nothing like this. They should be clumpy, messy, and irregular. They should be in the middle of cosmic puberty, awkward and unfinished. But Webb has been finding something different. Webb has been finding early galaxies with disks, with spirals, with organized rotating structures. Galaxies that by all rights should still be chaotic are instead smooth and elegant. Some of them look eerily like modern galaxies despite being only a fraction of the age. This was not predicted. This was not expected. And for a while, astronomers debated whether Webb was perhaps misinterpreting what it was seeing. Maybe the image resolution was tricking us. Maybe those shapes were illusions. But as more and more data came in, the pattern became clear. Disks were common in the early universe. Spirals were more common than anyone thought. And the process by which galaxies organized themselves into elegant shapes was happening far earlier than the old models predicted. Why does this matter? Because a galaxy that has a disk is a galaxy that has settled down. It has achieved a kind of gravitational equilibrium where the gas and stars are rotating in a stable plane. That kind of organization takes time. It takes many orbits. It takes the dampening of turbulence and the merging of smaller structures. To see disks so early is to realize that the early universe was not as turbulent as we thought, or that galaxies are capable of organizing themselves much faster than our simulations suggest. Again, this is not a failure of the standard model. It is a stretching of it. It is a reminder that the universe has its own way of doing things, and our models are always catching up. Webb is also helping us to understand what happens to some of these early galaxies over time. Because in some fields, the telescope has been able to catch galaxies in different stages of their development, early, middle, late. And by comparing these stages, astronomers can reconstruct what cosmic evolution actually looks like when viewed across billions of years. What they are finding is that many of the most impressive galaxies in the early universe did not survive. They merged. They got torn apart. They were absorbed into larger structures. The galaxy you saw at the beginning is not the galaxy you see at the end. Instead, the modern universe is built on the bones of countless older galaxies that were swept into bigger ones. The Milky Way itself, for example, is the product of many ancient mergers. It contains the ghosts of smaller galaxies that were pulled in long ago. You can still see traces of them in the motions of certain star clusters. This has a strange, almost poetic quality to it. The galaxies that dominate the modern universe are the survivors. They are the ones that grew, the ones that absorbed others, the ones that outlasted the chaos of the early cosmos. And Webb is showing us their ancestors, the small ones, the compact ones, the ones that became fuel for the great collisions to come. And here is another thought to sit with. Every photon of light that Webb captures from a distant galaxy is a time capsule. It left that galaxy billions of years ago. It traveled across the vacuum of space for nearly the entire age of the universe. It passed through regions of gas and dark matter. It was stretched by cosmic expansion. And finally, after an unimaginable journey, It landed on Webb's golden mirror and was captured for humanity to see. The galaxy that sent that light might no longer exist in the form we see it. It might have merged with another. It might have been torn apart. It might have evolved into something unrecognizable. But its light is still traveling, still carrying the memory of what it once was. And now, for the first time, we can read that memory. Let us return to the mystery of the little red dots, because there is more to that story than we have yet explored. And if we are going to make sense of what Webb has been showing us, we have to understand just how unusual these objects really are. When astronomers first began to catalogue the red dots in detail, they noticed something strange about their spectra. A spectrum, remember, is the rainbow of light broken apart, revealing the fingerprints of elements and the motions of whatever is emitting it. And when the spectra of the red dots were analysed, they did not look like any normal galaxy. They did not look like any normal star. They looked like a hybrid, like something that combined features of both. Some researchers propose that the red dots might contain active galactic nuclei, which are essentially actively feeding supermassive black holes surrounded by disks of superheated gas. Those environments are known to produce strong emission lines, particularly in hydrogen. And indeed, some of the red dots show those emission lines, but other red dots do not. Some of them look quite stable, and almost too calm for what is supposedly happening inside them. This inconsistency is important, because it suggests that the red dots are not all the same. There might be different populations of them. Some might be young galaxies with active black holes at their centers. Others might be something entirely different. And still others might be the exotic dark stars that theoreticians have predicted for decades. Imagine that for a moment. Imagine a single survey field, a tiny patch of sky containing 3 or 4 different categories of objects that we cannot yet tell apart. That is where we are right now. Webb has given us the images. It has given us the spectra, but it has not yet given us the clarity. And that clarity will come only with more observation, more analysis, and probably more new theories. And this is where the science starts to feel almost like detective work. Scientists are not just collecting data. They are following clues, trying to piece together a story from fragments. Every spectrum is a witness. Every image is a crime scene. And somewhere inside all of that information is the truth about how the first cosmic structures came into being. One of the most tantalizing clues came from a survey that caught several red dots in a region with unusually bright hydrogen emissions. These emissions suggested that whatever was inside the red dot was processing enormous amounts of hot hydrogen, either by feeding a black hole or by sustaining the fusion of an incredibly large star. The scale of the emission was huge. It implied an energy output that was difficult to explain with ordinary physics. One of the scientists involved in the study compared the red dots to cosmic question marks, because each one raises more questions than it answers. And that is the quiet thrill of modern astronomy. The feeling of staring at an image that contains more mystery than meaning, of knowing that somewhere in that speck of light is a piece of the universe's story that we have not yet learned to read. Now, let us shift our attention back to the wider implications. Because the discoveries Webb is making are not just adding to our understanding of the early universe, they are forcing us to reconsider how structure forms across all of cosmic history. One of the core assumptions in cosmology is the idea of hierarchical structure formation. This is the notion that small things form first and larger things grow out of them. Tiny dark matter, halos come together. Small galaxies are born inside them. Those galaxies merge into bigger ones. And over time, you end up with the great cosmic web we see today, where galaxies cluster along enormous filaments of dark matter spanning hundreds of millions of light years. But Webb is showing us that the small things may have grown bigger faster than the hierarchy predicted, or alternatively, that some of the large things were born large to begin with. The boundary between small and big is getting blurry. The idea of a slow, step-by-step growth is being challenged. And if hierarchical formation is not quite right, then the models that depend on it will need adjustment. That is a big deal, because those models are not just academic curiosities. They underpin everything from our estimates of dark matter distribution to our predictions of how galaxies evolve. If Webb forces us to revise them, it could ripple outward through the entire field, and it might change how we understand not just the early universe, but the present one as well. Here is another strange thought. Some of the galaxies Webb is finding in the early universe appear to already contain older stars, not newborn stars, not stars that formed in the last million years, older ones, stars that have had time to age, to evolve off the main sequence, to settle into their mature phases. In a galaxy that is only a few 100 million years old, how is that possible? One interpretation is that the first stars formed even earlier than we thought. Before the galaxies we are seeing came into being, there must have been a population of stars that lit up the universe and began producing heavy elements. Those stars eventually ended up inside the galaxies Webb is now detecting, which means that the era of the first stars may have begun in the first 100 million years after the Big Bang, possibly even earlier. That is an astonishing compression of time. It means the universe was igniting while it was still, in cosmic terms, an infant. And yet another interpretation is that the stellar evolution in those early environments proceeded differently. The first stars may have been far more massive than modern stars. They may have burned through their fuel in just a few million years. Their aging process may have been sped up. What looks like an old stellar population in a Webb spectrum may actually be a normal one that simply aged very quickly because of its unusual chemistry and size. Either way, the result is a picture of the early universe as an extraordinarily active place. A place where fuel burned quickly, where structure formed rapidly, where stars lived and died in compressed timescales. A place unlike the calm and patient universe we inhabit today. That contrast is worth holding on to, because the universe we live in now is remarkably quiet. Stars form slowly. Galaxies evolve over billions of years. Even black hole feeding has slowed significantly from its early peak. The cosmos has settled into a kind of mature middle age. But Webb is showing us the wild youth, the frenetic teenage years, the era when everything was happening all at once and at speeds we barely comprehend. And there is something comforting about that, even in its strangeness, because it reminds us that the universe has changed, that the rules we see today were not always the rules, that the cosmos we inhabit is the result of a long, complicated, beautiful process, and we are only just beginning to understand it. Speaking of changes, there is another thread in the Webb story that deserves attention, and that is the role of gas. In the early universe, the cosmos was filled with gas, mostly hydrogen, some helium, trace amounts of lithium. This gas was what stars were made of. It was the raw material for galaxies, and in the beginning, there was a lot of it, enormous clouds of it. Vast reservoirs spanning millions of light years. Over time, that gas got used up. Stars consumed it. Black holes ate it. Some of it got blown out of galaxies by supernovae. Some of it was heated to such high temperatures that it could no longer collapse into new stars. The early universe was gas-rich. The modern universe is relatively gas-poor, at least compared to its youth. Webb has been able to peer into regions of the early universe where gas still dominates, and it has found something interesting. The gas was not distributed evenly. It clumped, it flowed, it formed great streams that fed into the centers of forming galaxies like cosmic rivers. Those rivers delivered material to the heart of each structure, fueling black holes and igniting new stars. In some cases, Webb has even captured images of these streams in progress. Tendrils of gas reaching into a galaxy's center, feeding whatever is there. This matches some earlier predictions. Simulations had suggested that gas flows might be important in early galaxy formation. But seeing them in action is different. Seeing is always different. And those gas streams may also explain how the early black holes grew so fast. If they were being fed not by random collisions but by organized flows of cold gas from the cosmic web, they could have eaten continuously for millions of years. That kind of sustained feeding would push growth rates far beyond what random mergers would allow. The Eddington limit may still apply, but the feeding could have been more constant, more reliable, and more voluminous than previously thought. Picture it for a moment. A young black hole millions of solar masses already sits at the center of a cloud of forming structure. And from all directions vast threads of hydrogen and helium are streaming inward. Continuous rivers of raw material feeding the black hole year after year, decade after decade, millennium after millennium for millions of years. Never stopping, never running dry. The universe itself is funneling fuel to the heart of this monster. No wonder they grew so big. No wonder they grew so fast. But even with these explanations, we are still left with puzzles. We are still left with questions. And perhaps that is the most fitting thing about Webb. It does not close chapters. It opens them. Let us take a step back and think about what all of this means. Not scientifically, but philosophically. Because the universe Webb is showing us is not the tidy, orderly cosmos that fit neatly into our old models. It is something richer, something stranger, something with more layers than we expected. For centuries, human beings have tried to understand the sky. We have built telescopes, mapped stars, plotted the motions of planets, calculated the distances to galaxies. Each generation has added to the picture. Each new instrument has pushed the frontier a little further. And now, with Webb, we are looking at the oldest light the universe has ever produced, or at least the oldest light we have been able to reach so far. And what we are seeing is humbling. It is humbling because it shows us how little we know. We thought we had a rough outline of the early universe, and Webb is showing us that the outline was incomplete. We thought galaxies grew slowly. They do not always. We thought black holes took a long time to become supermassive. Some of them did not. We thought the first stars were sparse and scattered. They may have been abundant and concentrated. At every turn, our expectations are being gently corrected by the data. It is also humbling because it reminds us how much there is still to learn. The discoveries Webb has already made are only a fraction of what it will make over its lifetime. The telescope is expected to operate for many more years. It will survey more fields. It will study more galaxies. It will find things we cannot yet imagine. The mystery of the little red dots may be solved someday, or it may deepen. Either way, we will know more than we do now. And it is humbling because it gives us a glimpse of time on a scale we cannot fully comprehend. 13 billion years. That is how old some of the light Webb is catching is. 13 billion years of travel across cold, empty space. 13 billion years of patiently drifting toward our instruments. When you realize that the photons hitting the telescope's mirror were emitted before the Earth existed, before the Sun existed, before any of the elements that make up your body existed, it changes the way you feel about the present moment. You are here. The light is here. And somehow, despite the enormous distances and the immense time the two of you have met, there is a quiet magic in that. Let us come back to the scientific picture though, because there is one more thread we have not yet pulled, and it ties into everything we have discussed, and that is the question of dark matter. Dark matter is one of the great unknowns in physics. It makes up most of the matter in the universe, and yet we cannot see. It cannot touch. It cannot directly detect it with any instrument we have built so far. We know it exists because of its gravitational effects. Galaxies rotate as if they have more mass than we can see. Light bends around clusters as if it is being pulled by something invisible. The very structure of the cosmic web requires dark matter to hold it together. But what is it? Nobody knows. There are theories, weakly interacting massive particles, axions, sterile neutrinos, primordial black holes. Each of these possibilities has been proposed and studied, and each has its strengths and weaknesses, but none have been directly observed. Dark matter remains a placeholder, a name for something we know is there, but cannot yet identify. Now here is where Webb enters the dark matter story. Because if the dark star hypothesis turns out to be correct, and some of the little red dots really are powered by dark matter annihilation, it would be the first direct observational evidence of dark matter doing something, not just sitting there, gravitating, actually producing energy, actually affecting the luminous universe in a way we can measure. That would be historic. Even if the red dots are not dark stars, Webb is still helping us study dark matter indirectly. The distribution of galaxies in the early universe tells us how dark matter was distributed. The rate at which galaxies form tells us how efficient dark matter was at gathering gas. The shapes of galaxies and the velocities of their stars tell us how much dark matter they contain. Every Webb observation is in a sense a dark matter observation too, because dark matter is the invisible scaffolding on which everything else is built. And Webb's findings are putting new constraints on what dark matter can be. If structure formed faster than expected, that could mean dark matter is a little different from what we thought. Maybe its particles are slightly more massive, or slightly less interactive, or slightly more clumpy. Maybe the old models of dark matter behavior need revision. Maybe the long search for the identity of dark matter will take a new turn prompted by what Webb is showing us. There is a branch of physics called cold dark matter theory, which assumes that dark matter particles move slowly and clump together efficiently. Most of our models of galaxy formation rely on this theory. But there are alternatives. Warm dark matter, where the particles move faster and do not clump as easily. Fuzzy dark matter, where the particles behave like waves rather than points. Self-interacting dark matter, where the particles can collide with each other. Each of these alternatives would produce slightly different predictions for what the early universe should look like. Webb is helping us test those predictions, and the early results suggest that cold dark matter is still the best fit, but that the exact behavior of dark matter may be more complex than the simplest version of the theory implies. There may be subtleties. There may be hidden dynamics. The door is open for new discoveries. Let us also consider something else. The universe Webb is showing us is not just strange in its content. It is strange in its rhythm. By that I mean the pace at which things happened. In the old story, the early universe was a gradual affair. Slow cooling, slow clumping, slow ignition, slow growth. Everything took time. The image of the early cosmos was a kind of cosmic twilight slowly brightening into morning. The new story is different. The new story is fast. Rapid cooling as the universe expanded and temperatures plunged. Rapid clumping as dark matter gathered gas. Rapid ignition as the first stars flared to life across vast regions simultaneously. Rapid growth as galaxies assembled and black holes feasted. The universe was not a slow morning. It was an explosive dawn. The sky lit up quickly. And this new pace has implications for something called the reionization era. This is the period when the first stars and black holes began producing enough ultraviolet light to ionize the neutral hydrogen that filled the early universe. Before reionization, the universe was foggy. Hydrogen atoms absorbed ultraviolet light, making it hard for radiation to travel far. After reionization, the universe became transparent. Light could flow freely across vast distances. It was like lifting a veil. Reionization was a turning point. It was the moment the universe became truly visible. And Webb is showing us what caused it. The first massive galaxies, the early black holes pumping out radiation, the population 3 stars that burned so intensely they ionized the gas around them. All of these things combined to clear the cosmic fog. And Webb is letting us watch the process unfold. In some fields, Webb has even caught what astronomers call ionization bubbles. These are regions where the hydrogen has been fully ionized surrounding sources of strong ultraviolet light. Over time, these bubbles grew and merged, eventually filling the entire universe with transparent space. The bubble stage lasted hundreds of millions of years, and it is during that period right in the middle of reionization that most of the Webb anomalies are appearing. This is not a coincidence. The same processes that drove reionization also produced the earliest massive galaxies, the feeding black holes, and possibly the little red dots. Everything is connected. Everything is part of the same story. And Webb is slowly helping us read that story from beginning to end. There is one more concept that deserves our attention. It is a strange idea, and it is still being debated, but it may hold part of the answer to why the early universe looks so mature. The idea is called cosmological feedback, and it refers to the way early stars and black holes influence the gas around them. When a massive star explodes, it does not just spread elements, it also blasts the surrounding gas with energy. That energy heats the gas, pushes it outward, and slows future star formation in that region. When a black hole feeds it, emits radiation and jets of particles that do the same thing on a much larger scale. The result is a kind of cosmic thermostat. As galaxies grow, their own energy output regulates how quickly they continue to grow. This feedback is thought to be extremely important in shaping galaxies. Without it, galaxies would grow uncontrollably large, and we would see very different structures in the universe today. The presence of feedback explains why galaxies stop at certain sizes, why black holes and their host galaxies seem to be correlated in mass, and why there is a limit to how much gas any given galaxy can turn into stars. But in the early universe, feedback was different. It was weaker, or sometimes stronger, or sometimes simply delayed. And that created unusual conditions that could have allowed some galaxies to grow much bigger than they should have, while others were suppressed. Webb is now looking at these effects directly. It is watching feedback in action. It is seeing how different early galaxies handled the energy pouring out of their stars and black holes. And the picture is complex. Some early galaxies seem to have experienced brief but intense periods of feedback, which shut down their growth quickly. Others seem to have escaped feedback, somehow growing unchecked into the massive structures we see in the surveys. The variation is striking. It suggests that the early universe was not a uniform place. It had regions of calm and regions of chaos. It had galaxies that lived on the edge of stability and galaxies that burned out fast. This variation may also help explain why Webb is finding some galaxies that look old and others that look young in the same era. Because the speed at which a galaxy grows depends on how well it can manage the feedback from its own stars and black holes. Some galaxies got the balance right early on and settled into smooth, organized disks. Others never did and remained chaotic and irregular until they were absorbed into something larger. It is a reminder that the early universe was not a single story. It was many stories. Millions of different galaxies, each evolving in its own way, each subject to its own local conditions, each carving out a different path through cosmic history. And Webb is letting us see the entire range, from the earliest anomalies to the smoothest survivors. Now let us turn to something that has received a lot of attention recently, and that is the idea that Webb may be revealing what some astronomers are calling early mature galaxies. These are objects that, despite forming within the first few 100 million years of the universe, already look like they belong in our modern neighborhood. They are rotating. They are organized. They have features that took our own Milky Way billions of years to develop. The existence of early mature galaxies is a particular kind of puzzle, because maturity in a galactic sense implies a long history. It implies merging, settling, and evolving. It implies that a galaxy has been through many cycles of star formation and chemical enrichment. How do you get that kind of maturity in a universe that is still so young? The answer, according to some theorists, is that the early universe may have been capable of producing galaxies that skipped certain evolutionary stages. Instead of starting as small, chaotic blobs and gradually assembling into larger structures, some galaxies may have formed all at once from a particularly dense region of dark matter and gas. These galaxies would have been born large-born, structured, and born ready to evolve quickly. They would not have had to wait for mergers to grow. They would not have had to deal with the long process of chemical enrichment. They could have done everything quickly, almost in parallel. This is sometimes called the monolithic collapse model. It is an old idea, actually. It was proposed back in the early days of galaxy formation theory, before hierarchical assembly became the dominant paradigm. But Webb's findings are making some astronomers revisit it. Maybe the old idea was partly right. Maybe some galaxies really did form monolithically, while others formed hierarchically, and the actual cosmic history is a mix of both. If that is the case, then the story of cosmic evolution becomes richer. It means there are multiple pathways to becoming a galaxy, multiple ways to end up massive, structured, and mature. And Webb is letting us see those pathways diverge in the earliest eras of the universe. Let us also think about our own galaxy in light of all this. The Milky Way is a fairly typical large spiral. It is massive, but not the most massive. It is old, but not the oldest. It has experienced many mergers over its life, absorbing smaller galaxies and growing in the process. Its history is visible in the motions of its stars, the distribution of its dark matter, and the composition of its different regions. So where did the Milky Way come from? If Webb is showing us the early universe in such detail, can it help us understand the origins of our own galaxy? The answer is yes, but indirectly. We cannot see the Milky Way's ancestors directly because they are long gone. Whatever galaxies merged to form the Milky Way were consumed billions of years ago. But Webb can show us similar galaxies in the early universe, galaxies that resemble the probable ancestors of our own. And by studying them, we can reconstruct with increasing precision what our galactic origins may have looked like. In this sense, Webb is doing something incredible. It is giving us access to our own past, not just the human past, not even just the Earth's past, but the past of our entire cosmic home, the lineage of the galaxy that gave birth to the Sun, the planets, and eventually us stretches back more than 13 billion years. And Webb is the first instrument capable of showing us those earliest chapters. It is like finding a photograph of your ancestors from a time before photographs existed. A strange, wonderful impossibility. And yet for all of this, the mysteries remain. We still do not know what the little red dots actually are. We still do not know why some black holes grew so fast. We still do not know why the chemistry of certain early galaxies is so enriched. We still do not know if our timeline for the Big Bang is correct. We still do not know if dark matter can power stars. Every answer Webb gives us seems to come packaged with a new question. And this is exactly what good science does. It opens up new avenues for exploration. It does not pretend to have all the answers. It embraces the unknown and uses it as fuel for the next investigation. Some of Webb's observations have even hinted at things stranger than the red dots. In a few of the deepest fields, astronomers have reported faint signals that do not match anything we know. Not stars, not galaxies, not black holes. Just strange diffuse glimmers of infrared light that seem to come from regions where nothing should exist. These signals are still being analyzed. They may turn out to be instrumental artifacts. They may turn out to be faint, distant objects too dim to classify. Or they may turn out to be something new, something we have not yet imagined. It is too early to say, but the possibility is there. The possibility that Webb has shown us things we do not yet have names for. And the history of astronomy is full of moments like that. Every major telescope from Galileo's first spyglass to the Hubble has detected phenomena that took decades to understand. Quasars, pulsars, gravitational lenses, dark energy. All of them started as puzzles. All of them began as flickers of strange light that no one knew how to classify. Webb may be adding its own puzzles to that tradition. And maybe decades from now, the things that confuse us today will be obvious. Textbook knowledge, standard fare for every new astronomer learning about the early universe. We will remember these years the way modern astronomers remember the first quasar observations, as the moment when the rules began to bend. Let us dwell for a while on one of the most poetic ideas to come out of Webb's discoveries. The idea that we are in a very real sense witnessing the childhood of the cosmos. Think of what that means. A childhood is not just a period of physical growth. It is a period of formation, of patterns being laid down, of character being shaped. The early universe was in a state of becoming. It was not yet what it would later be. And Webb is letting us watch that becoming unfold. We see galaxies taking their first shapes. We see black holes having their first meals. We see chemistry being established. We see gas streams funneling into the densest regions and igniting new generations of stars. Each image is a snapshot of the universe learning how to be itself. And we are here billions of years later looking back with instruments delicate enough to capture individual photons that left their sources before our solar system existed. It is an astonishing privilege. It is the kind of perspective that our ancestors could not have imagined, and that even the astronomers of a century ago could only have dreamed about. Now let us also consider something quieter, something less dramatic, but no less important. And that is the discovery of what appears to be normal galaxies in the early universe. Galaxies that look just like modern galaxies, not huge, not unusually massive, not anomalous, just ordinary spirals and ellipticals going about their business. This sounds unremarkable, but it is actually fascinating. Because the existence of normal galaxies in the early universe tells us something important. It tells us that the physics of galaxy formation has always been the same. That the basic rules of stars and gas and gravity applied as much 13 billion years ago as they do today. That the cosmos, for all its strangeness, has a consistent underlying fabric. The anomalies Webb is finding are real, but they exist alongside a population of perfectly ordinary objects, galaxies that fit the predictions, black holes that grew at expected rates, stars that formed when they were supposed to. The early universe was not entirely wild. It had its calm neighborhoods too, its quiet patches, its normal galaxies doing normal things. This mixed picture of anomalies and ordinaries coexisting may be the most realistic portrait of the early universe we have ever had. It shows us a cosmos that was capable of producing the strange, but also committed to the normal. A cosmos where the rules were reliable, but where the conditions occasionally pushed those rules to their limits. And that is where the interesting physics happens. At the limits, at the edges, where normal becomes strange, where the expected gives way to the unexpected. Webb is showing us those edges in unprecedented detail. Let us also talk about what Webb does not show us, because that matters too. Webb cannot show us the Big Bang itself. No telescope can. The Big Bang was an event so hot and dense that no light could escape it for hundreds of thousands of years. The oldest light we can ever see is the cosmic microwave background, which was emitted about 380,000 years after the Big Bang, when the universe finally cooled enough for light to travel freely. That background radiation is what instruments like the Planck satellite and the Cosmic Background Explorer have mapped in detail. It is the baby picture of the cosmos. Webb cannot see back to that moment, but it can see almost everything after. It can see the first stars, the first galaxies, the first black holes, the first heavy elements, the first organized structures. Everything that happened after the microwave background lifted Webb is capable of observing, and that is an enormous span. Most of the universe's interesting history happened after that veil cleared, and Webb is our best window into it. One thing that often surprises people is how slow these discoveries actually are. Webb is not showing us the early universe in real time. It is building a picture piece by piece, field by field, spectrum by spectrum. A full analysis of a single early galaxy can take months. A proper study of a population of red dots can take years. The Webb science team is still working through data from the telescope's first few years of operation, and new results are coming out every week. And that is how astronomy works. Slowly, carefully, patiently. The dramatic moments we see in the news are usually the tip of a very long iceberg. Behind every headline is a team of scientists who have spent a huge amount of time verifying, checking, and cross-referencing their findings. Behind every image is calibration. Behind every spectrum is analysis. The universe does not give up its secrets easily. But with Webb, we have the tools to keep asking, keep measuring, keep looking. Let us imagine for a moment what the next decade of Webb observations might bring. The telescope is expected to operate for at least another 15 years, possibly longer. In that time, it will survey many more deep fields. It will study thousands more galaxies. It will measure spectra for objects we have not even identified yet. The catalogue of early universe discoveries will grow enormously. And with each new data set, our understanding will sharpen. Among the things we might expect are clearer answers about the little red dots, better estimates of early black hole masses, more detailed maps of reionization, deeper spectra of early galaxies, possibly even direct detections of population 3 stars. Maybe, if we are lucky, confirmed observations of dark stars, or maybe something entirely new. Something we have not yet thought to look for. This is the great gift of a good telescope. It does not just answer your questions, it teaches you how to ask better ones. And Webb is teaching us how to ask better questions about the beginning of everything, about how time unfolded, about how matter organized itself, about how light filled the void, about how chemistry became possible, about how galaxies emerged from the dark, about how black holes formed and fed and grew, about how we eventually came to be. These are enormous questions. They have been asked by humans for as long as we have looked up at the sky. But now, for the first time, we have a tool capable of bringing back real specific testable answers. Not stories, not myths. Actual observations of the earliest moments of the visible universe. Actual data, actual spectra, actual images. That is a gift of science, a gift of engineering, a gift of decades of patient work by thousands of people around the world. Webb was built over many years with budget problems and delays and setbacks at every stage. It was almost cancelled. It was almost abandoned. But the scientists and engineers persisted. They refused to let it go. And because of their persistence, we are now living in an era of cosmic discovery that previous generations could only have dreamed of. Every new Webb image is in a way a love letter to that persistence, to the patience of the builders, to the stubbornness of the dreamers, to the quiet devotion of people who believed that understanding the universe was worth any effort, any cost, any struggle. And now the results are pouring in one image at a time. We live in a strange and wonderful moment. We can look back more than 13 billion years. We can see the first galaxies. We can measure the feeding of early black holes. We can detect traces of stars that have been gone for eons. We can peer into the chemistry of objects that should not exist. And every time we do, we learn something new. And through all of it, one thing remains true. The universe is bigger, stranger, and more beautiful than we knew. And every step toward understanding is also a step toward wonder. Let us now move into a different part of the story. Let us talk about what Webb has revealed about distances, because one of the most challenging aspects of studying the early universe is simply figuring out how far away something is. And distance in cosmology is everything. When we say that a galaxy is 13 billion years old, what we really mean is that its light took 13 billion years to reach us. That is a different thing from the galaxy itself being 13 billion years old. The object might no longer exist. Or it might have evolved into something unrecognizable. But the light we are seeing, the photons arriving at Webb's mirror, left the galaxy when the universe was very young. So in a sense, we are seeing the galaxy as it was long ago, a time capsule of light. Measuring this distance is tricky. Astronomers use something called redshift to estimate how far away a cosmic object is. The basic idea is that as the universe expands, it stretches the light traveling through it. A galaxy moving away from us emits light that appears redder than it would if the galaxy was standing still. The more distant the galaxy, the more its light has been stretched. By measuring how much a galaxy's spectrum has shifted toward the red end, astronomers can calculate how far away it is and how long ago its light was emitted. Webb is particularly good at measuring redshift because it sees in infrared. Highly redshifted light that would look invisible to a visible light telescope is exactly what Webb is designed to detect. That is why it can reach objects no previous telescope could. That is why it can push past the wall where Hubble's vision ended. But here is where it gets interesting. Some of the redshifts Webb has been measuring are extreme. So extreme that they place the galaxies in question at distances corresponding to the first 300 million years of cosmic history. That is an enormous look-back time. And the fact that Webb can make those measurements reliably is a triumph of instrumentation. Yet the extreme redshifts also raise questions. Because if the galaxies are that far away, and that massive and that structured, then either the universe was producing massive galaxies in its first 300 million years, or our redshift estimates are wrong. This has led to some debate. Are the extreme redshifts real? Or are they being inflated by dust? Or by unusual spectral features? Or by some subtle effect that has not yet been accounted for? A few papers have suggested that some of Webb's early redshift measurements may have been overestimated, that the galaxies are actually a bit closer and a bit less extreme than initially reported. But other researchers have defended the extreme values. They have argued that the measurements are solid, that the galaxies are really that far away, and that the early universe really did build massive things faster than we predicted. The debate is ongoing, and with each new observation, the picture sharpens a little more. The truth almost certainly is somewhere in between. Some of the extreme redshifts are probably accurate. Some are probably a little overestimated. And together, they paint a picture of an early universe that is more active, more productive, and more structured than we thought, even if not every individual claim holds up to scrutiny. This is how science works. Claims are made, claims are tested, claims are refined. Over time, a consensus emerges, and it usually lies somewhere between the initial excitement and the initial skepticism. And with Webb, we are still in the early stages of that process. The exciting discoveries are coming in fast. The careful analysis is still catching up. Let us also think about what Webb means for the field of observational cosmology more broadly, because Webb is not the only instrument studying the early universe. There are radio telescopes like ALMA, the Atacama Large Millimeter Array, that can see the cold gas in distant galaxies. There are other space telescopes like Euclid and Roman, which are mapping the large-scale structure of the universe with different techniques. And there are ground-based observatories with adaptive optics that can now match the resolution of space telescopes in certain wavelengths. Together, these instruments form a kind of distributed observation network. Each one contributes something different. Each one sees the universe in its own way. Webb provides infrared sensitivity and deep field imaging. ALMA provides cold gas maps and molecular spectra. Euclid provides wide-angle surveys of dark matter distribution. Roman provides high-resolution studies of distant supernovae. And the ground-based observatories provide continuous monitoring of changing objects. When all of these tools are pointed at the same regions of the sky, the result is a multi-layered map of the early universe. A map that no single instrument could produce on its own. And it is from this combined effort that our best understanding is emerging, not from any one telescope, but from the cooperation of many. Webb is in that sense a key piece of a larger puzzle, a vital piece certainly, perhaps the most important new piece in a generation, but not the only piece. And the real breakthroughs will come when we combine Webb's data with data from all the other instruments working alongside it. There is something deeply collaborative about modern astronomy. It is not the image of a lone scientist peering through a telescope in a mountain observatory. It is a global network of researchers sharing data, pooling resources, challenging each other's findings, and collectively building a picture of the universe that no single person or institution could create alone. Webb is part of that network. Its data is shared publicly, typically after a short proprietary period. Anyone in the world with the skills to analyze it can contribute to understanding what Webb has seen. and many people do. Every week, new papers appear based on Webb data. Every month, new insights emerge. This openness is one of the most remarkable aspects of the Webb project. The telescope is not a private resource. It is a public one, paid for by international cooperation, shared across national boundaries, used by researchers from every continent. The discoveries that come from it belong to humanity as a whole. And that feels like a fitting tribute to the scale of what Webb is observing. The universe, after all, does not belong to any one of us. It belongs to all of us. Or perhaps more accurately, we all belong to it. Let us shift our attention now to another fascinating aspect of the early universe, something that connects directly to the little red dots and the mystery of early structure. And that is the concept of the first black holes. Black holes, as we discussed, seem to have been active and hungry in the early universe. But how did they form in the first place? What kind of process creates a black hole from scratch in a universe that is only a few 100 million years old? The traditional answer is that black holes form from the collapse of massive stars. A giant star dozens of times the mass of the Sun runs out of fuel. Its core collapses under its own gravity. If the star is massive enough, the collapse becomes unstoppable and a black hole is born. These stellar mass black holes are common in the modern universe. We know they exist. We have observed them merging, detecting their gravitational waves. But stellar mass black holes are small. They start out at roughly 10 times the mass of the Sun. To grow to 1 million or 1 billion solar masses, they need time. They need fuel. They need mergers, lots of them. And even under ideal conditions, the timescales are long. The early universe does not seem to have had the luxury of those timescales. And so astronomers have proposed other pathways to early black holes. One pathway is direct collapse. This is the idea that a very dense cloud of pristine hydrogen gas, in just the right conditions, can skip the stellar phase entirely and collapse directly into a black hole. The resulting object would have a much higher starting mass, perhaps tens of thousands of solar masses. From there, it could grow more quickly, because it already has a significant head start. Direct collapse requires specific conditions. The gas cloud has to be massive. It has to be free of heavy elements, which would otherwise cool it and cause it to fragment into stars. And it has to be situated near a strong source of ultraviolet radiation, which prevents molecular hydrogen from forming. Those conditions are rare but plausible in the early universe. And if they were met, even in a few places, the seeds of supermassive black holes could have been planted very early. Another pathway is through the merging of many smaller black holes in dense stellar clusters. In such environments, black holes can fall toward the center of the cluster, meet other black holes, and merge. Each merger increases the mass. Over time, a central black hole could grow to substantial size by repeatedly consuming its neighbors. If this happened in many clusters simultaneously across the early universe, it could explain the early appearance of supermassive objects. And then, there is the most radical pathway: primordial black holes. These would be black holes formed not from stars or gas clouds, but from fluctuations in the very early universe itself. During the first instance after the Big Bang, the density of matter was not perfectly uniform. There were slight variations. If any of those variations were extreme enough, regions of space may have collapsed directly into black holes without any stellar or galactic precursor. Primordial black holes would be a class of their own, born in the chaos of the Big Bang, ancient from the moment they existed. Primordial black holes are still hypothetical. We have not confirmed their existence. But they are a real possibility, and some models suggest they could account for some fraction of dark matter. Or they could be the seeds of the first supermassive black holes. Or they could be something else entirely. If Webb ever detects one directly, it would be a discovery of immense significance. And that is one of the things Webb could in principle do. By studying very high redshift objects in detail, Webb might find anomalies that point to the existence of primordial black holes, tiny ancient massive objects with no obvious stellar or galactic origin, objects that simply cannot be explained by any other process. Webb has not yet definitively found any, but the search continues and the data is improving. As we reflect on all of this, it is worth pausing to appreciate just how much Webb has changed in a short time. The telescope has been operational for only a few years, and yet, in that brief period, it has transformed our understanding of the early universe. It has given us new objects to study, new questions to ask, new mysteries to chase, and new hope that we might one day understand how everything began. Compare that to the timescale of cosmic evolution. 13 billion years, the time it took for the universe to go from hot plasma to complex life on a small blue planet. That is the scale Webb is measuring. That is the distance it is bridging. And it is doing so with a telescope that took decades to build and that has only just begun its real work. The next few years will be extraordinary. More surveys will be completed. More anomalies will be catalogued. More theories will be tested. And somewhere in all of that, we will likely encounter something that surprises us even more than the little red dots have. Because that is the nature of discovery. It is never quite what you expected. It is always a little stranger, always a little richer, always a little more humbling. Let us think for a moment about what the very first star might have looked like. The first star in the universe. The one that came before all others, before any galaxies, before any heavy elements, before any complex structures. Just one lonely object igniting for the first time in a universe that had been dark for millions of years. That star, if it existed alone, would have been enormous, probably hundreds of times the mass of the Sun. Without any heavy elements to help cool the gas around it, the cloud that formed it would have been unusually hot, and the resulting star would have had to be massive to overcome that heat. It would have burned bright and fast. It would have died in a spectacular explosion, possibly leaving behind a black hole. And in its death, it would have spread the first heavy elements into the surrounding gas, paving the way for the next generation of stars. We will probably never see that first star directly. It was too brief, too small, and too distant to be captured by any telescope we can build in the foreseeable future. But Webb may come close. Webb may detect the chemical signatures of its descendants. Webb may see galaxies that contain stars that formed in the shadow of that first one. And in that sense, we may see its legacy, even if we cannot see the star itself. This is one of the quiet wonders of Webb. It is not just looking for the dramatic. It is looking for the quiet fingerprints of a cosmic past that would otherwise be invisible to us. The subtle emission lines, the faint spectral features, the small variations in galaxy shape or color that together tell a much bigger story. Let us come back to the little red dots one more time. Because as more data has come in, new interpretations have been proposed. Some astronomers now think the red dots are best explained as a mixed population. Most of them are probably compact dusty galaxies with active black holes at their centers. The dust absorbs visible light and re-emits it in infrared, giving the objects their characteristic reddish color. The active black holes provide the necessary energy output to explain their apparent luminosity, and the compactness can be explained by their early age. They had not yet had time to spread out into the larger, more diffuse shapes of modern galaxies. This interpretation is consistent with many of the observations. It does not require any exotic physics. It fits reasonably well within the standard model of galaxy formation. And it explains most of what Webb has seen. But it does not explain all of it. Some red dots have features that do not fit the compact dusty galaxy picture. Some show unusual spectra that are hard to reconcile with active black holes. Some are too dim in certain wavelengths and too bright in others. And a small subset matches the predicted signatures of dark stars with remarkable precision. So the working theory at this point is that the red dots are not one thing. They are several things. A category of objects that share some surface features but have different internal structures. Some are galaxies. Some might be single massive objects. Some might be rare exotic phenomena. And the challenge for the next few years of Webb observation is to figure out which is which. This is how knowledge progresses, slowly, carefully. With refined categories replacing broad strokes, with distinctions emerging where there used to be a single label. The red dots are no longer just the red dots. They are becoming a rich and varied family of cosmic objects, each with its own story to tell. There is another idea that has come up recently which I find particularly fascinating, and it relates to the possibility that the early universe had regions of unusual gravity. In general relativity, gravity is caused by the curvature of space-time in response to matter and energy. In the modern universe, space-time is fairly smooth on large scales. Gravity behaves predictably, but in the early universe things may have been different. The density of matter was higher, the variations in density were larger, and the dynamics of expansion were more intense. Some theorists have wondered whether regions of the early universe may have experienced slightly different gravitational conditions than we see today. Not wildly different, just subtly off from the modern baseline. If that is true, it could help explain some of the Webb anomalies. Slight variations in gravity could have sped up structure formation in certain regions, or it could have allowed certain dense objects to exist in forms that would be unstable in the modern universe. This is still speculative. It is not mainstream, but it is a possibility that some researchers are beginning to take seriously. And Webb's observations could in principle help constrain how much variation was possible. Related to this is the idea of modified gravity. Some theorists have proposed that the standard laws of gravity may need modification on certain scales. In particular, on galactic and cosmic scales, modified gravity theories attempt to explain some of the same observations that dark matter is usually invoked to account for. If modified gravity is correct, then the early universe might have behaved slightly differently than standard models predict, and Webb's data might be able to distinguish between the various possibilities. This is a controversial area of research. Modified gravity has its supporters and its critics. Most astronomers still favor the standard model with dark matter. But Webb is putting pressure on the standard model in subtle ways. And if that pressure continues to build, alternative theories might get more attention. Again, none of this is settled. None of this is conclusive. But it shows how Webb is not just confirming what we knew. It is also giving us reasons to question things we thought were already understood. It is making the field of cosmology more open, more dynamic, and more uncertain. And that is a healthy thing. A field that is too certain is a field that is not growing. Let us now consider what Webb has taught us about the diversity of the early universe. Because one of the most striking things about the discoveries is just how varied they are. There are galaxies that look ordinary. There are galaxies that look extraordinary. There are tiny compact objects. There are large diffuse ones. There are bright active feeders. There are quiet stable observers. There are structured disks. There are chaotic blobs. There are objects that fit the models. There are objects that defy them. And all of this variety exists within the same era of cosmic history. This tells us something profound. It tells us that the early universe was not a single kind of environment. It was many kinds. It was a patchwork, a mosaic, a collection of different local conditions that produced different kinds of objects. Some regions had more gas, some had less. Some had more dark matter, some had less. Some were denser, some were sparser. And each region produced what it could based on the local conditions. This variety is a reminder that cosmic history is not a single story. It is many stories running in parallel. The story of one galaxy is not the story of another. The story of one black hole is not the story of another. Each object has its own trajectory, its own moments of brightness and quiet, its own relationship with its neighbors. And by studying many of them, we slowly assemble a picture of the cosmic whole. Webb is helping us do that, not by showing us a simple narrative, but by revealing the messy, complex, beautiful truth of a universe that was always more diverse than we imagined. Let us take a moment to reflect on what it means to see so far, to see across billions of years of time, to catch photons that have traveled since before our sun existed. There is something almost meditative about considering it. Every image Webb sends back is a journey through time. Every galaxy it captures is a reminder that the universe is older, vaster, and deeper than any of our everyday experiences suggest. And yet, despite all that vastness, despite all that time, the universe is still connected. The light that Webb captures today left its source in a different era, but that source and our telescope are linked by a continuous thread of space-time. The photon did not teleport. It traveled. It moved inch by inch, mile by mile light, year by light year across the gulf, between that distant galaxy and our own solar system. And during that entire journey, the universe was expanding, evolving, changing. The photon had to survive all of that. It had to pass through the cosmic web, through filaments of dark matter, through forests of gas, through countless gravitational interactions. And somehow, after all of that, it arrived. It is a small miracle, not the kind that requires any supernatural explanation. Just the ordinary miracle of physics and time. But it is a miracle nonetheless, because it means we are not cut off from the early universe. We are connected to it. Its light still reaches us. Its story is still arriving. And with Webb, we finally have the instrument to read that story clearly. There are moments in human history when our understanding of the universe takes a leap forward. When Galileo pointed his small telescope at Jupiter and saw its moons. When Hubble looked at Andromeda and realized it was its own galaxy. When the Hubble Space Telescope imaged the deep field and showed us just how crowded the cosmos really is. Each of these moments reshaped our sense of scale, our sense of self, our sense of place in the universe. Webb is producing its own moment. Right now, in real time. Every new image, every new spectrum, every new surprising discovery is adding to a collective understanding that is evolving faster than any of us can keep up with. The textbooks are changing. The models are being rewritten. The frontier is shifting. And we are watching it happen. What is our place in all of this? That is a question worth pausing on. We live on a small rocky planet, orbiting an average star in a modest galaxy, in a cluster of galaxies that is one of many. We are late arrivals in cosmic history. The universe was already 9 billion years old by the time our solar system formed. Life on Earth is a few billion years younger than that. And human civilization is younger still, just a few thousand years in a universe that is over 13 billion years old. And yet, despite all of that smallness, we have built instruments capable of looking back to the beginning. We have developed theories capable of describing the large-scale structure of space and time. We have trained ourselves to read the faintest signals across the vacuum. We are in our own modest way cosmic archaeologists, reading the past from the light it left behind. There is something deeply human about that, something that connects us to every generation that came before every mind that looked at the night sky and wondered what was out there. Every person who ever asked how the universe began. Every curious child who stared at a starry sky and felt the pull of something unnameable. We are part of a long chain of wonder. And Webb is one of the tools by which that wonder is being translated into knowledge. It is easy when reading about cosmic discoveries to feel overwhelmed, to feel small, to wonder what all of this has to do with our daily lives. And the truth is, on a practical level, not much. Understanding little red dots will not help you pay your rent. Knowing about primordial black holes will not affect your commute. The anomalies of the early universe have no direct bearing on most of what makes up a human life. But on a deeper level, these discoveries matter. Because they are part of how we understand ourselves. They expand our sense of what is possible. They remind us that the universe is not finished revealing itself. They invite us into something larger than our individual concerns. And in a world that often feels fragmented and small, that invitation is worth accepting. Now let us return once more to the specific discoveries at hand. Because there is another aspect of Webb's findings that we have not yet explored in detail, and that is the role of dust. Dust, in astronomical terms, is not what you sweep off your shelves. It is microscopic particles of carbon, silicon, iron, and other heavy elements that are scattered throughout space. Dust is produced by dying stars, particularly supernovae and late-stage giants. It accumulates in interstellar space. It absorbs certain wavelengths of light. It re-emits that light in infrared. And it plays a huge role in shaping what we see when we look at distant galaxies. In the early universe, dust should have been rare. The first generations of stars had not yet had time to produce much of it. The heavy elements that make up dust had not yet been widely distributed. By all accounts, the earliest galaxies should have been relatively dust-free. But Webb has been finding dust where none was predicted. Some of the earliest galaxies Webb has observed contain substantial amounts of dust, much more than expected for their age. This is a puzzle in its own right. How did these galaxies accumulate so much dust so quickly? How did the heavy elements that make up the dust get distributed throughout the galaxy so early? One possibility is that the first generations of stars were extremely massive, and their supernovae produced enormous amounts of dust in short bursts. Another possibility is that dust forms more efficiently in certain conditions than we realize. Another is that there are more hidden stellar populations in these galaxies than we have yet detected quietly producing dust at rates we cannot easily measure. The presence of early dust also has observational implications. Because dust can obscure some of the light from early galaxies, the galaxies we can see may only be part of the total population. There could be many more early galaxies hidden behind clouds of dust, their light absorbed and re-emitted in ways that make them hard to detect. Webb is optimized for infrared, so it can see through some dust, but not all of it. There are probably ancient galaxies out there that even Webb cannot easily study, and that realization is humbling too. It means that the early universe may have been even more active, more productive, more populated than Webb is showing us. That the anomalies we see are just the visible tip of a larger population of hidden objects, and that the real story of cosmic evolution may be richer and more complex than any current telescope can reveal. Let us also touch on another theme, the theme of transformation, because the early universe was a place of rapid transformation. It changed quickly. Gas became stars, stars became galaxies, galaxies merged, black holes fed, radiation cleared the fog, heavy elements were spread, structures organized themselves. Everything was in motion, everything was changing, everything was becoming. And that transformation has not stopped. It continues today, just at a slower pace. Stars are still being born. Galaxies are still merging. Black holes are still feeding, if more gently. The universe is still transforming. It is just doing so more quietly than before. Our own Milky Way is on a trajectory that will eventually lead to a collision with the Andromeda Galaxy. The collision will take billions of years to unfold. It will produce new stars, new gravitational disturbances, new mergers of smaller structures. And eventually, the two galaxies will become one, a new mature galaxy born from the union of two. Our Sun, meanwhile, has billions of years of stable burning ahead of it, but eventually it too will transform. It will expand. It will shed its outer layers. It will become a dense white dwarf surrounded by the ghost of its former self. That will be the end of our solar system in its current form. A distant future, but inevitable. And all of this transformation is part of the same ongoing cosmic story that Webb is helping us to read from its earliest chapters. The changes that happen now are echoes of the changes that happened then. The processes that formed the first galaxies are the same processes that will one day transform ours. The universe is consistent in that way. It follows its own laws. It does what physics allows. And physics, so far as we can tell, is the same everywhere. There is a comfort in that consistency, even in its strangeness. The universe is not arbitrary. It is not random. It has a logic. And even when that logic produces objects we do not yet understand, like the little red dots, the logic is still there. We just have not yet cracked it. Cracking that logic is the work of the coming decades. And while Webb will play a huge role in that effort, it will not be the only instrument. New telescopes are being planned. New theoretical frameworks are being developed. New computational models are being built. The field of cosmology is in a period of extraordinary activity, and the pace of discovery is only accelerating. One of the most exciting upcoming missions is a telescope called the Nancy Grace Roman Space Telescope. It is scheduled to launch in the coming years, and it will complement Webb by surveying much wider areas of the sky. Where Webb focuses on deep fields and detailed spectra, Roman will map the large-scale structure of the universe. Together, they will give us both the big picture and the fine details, both the forest and the trees. There is also a concept for a future space telescope that would be even larger than Webb, sometimes called the Habitable Worlds Observatory, or other similar names. This hypothetical mission would be dedicated to finding and characterizing Earth-like planets around other stars. While its primary purpose would be exoplanet research, it would also contribute to cosmological studies by providing extremely high-resolution imaging of distant galaxies. And on the ground, new generation telescopes are under construction. Massive instruments with mirrors tens of meters across, capable of studying the universe in ways that have never been possible before. These telescopes will work alongside Webb, providing independent confirmations of its discoveries and extending its capabilities into new wavelengths. The future of cosmological observation, in other words, is bright. Not just because of Webb, but because of the entire ecosystem of instruments and ideas that Webb is part of. And as that ecosystem matures, our understanding will deepen in ways we cannot fully predict. Let us also think briefly about what Webb might mean for questions beyond pure cosmology, because the discoveries it is making touch on issues that extend into philosophy, into metaphysics, into the very foundations of how we think about time and existence. If the universe is producing mature galaxies earlier than expected, what does that say about the arrow of time, about the relationship between cause and effect, about the limits of our predictive models? Every discovery that challenges our timeline challenges our sense of how the universe works. It invites us to reconsider assumptions we did not know we were making. And if dark matter turns out to do more than we thought, if it can power stars or seed black holes, or shape the very structure of the early cosmos, then our picture of the material universe becomes more complex. It becomes stranger. It becomes more difficult to encapsulate in simple terms. We will need new concepts, new categories, new vocabulary, just to describe what is out there. This is how knowledge grows, not just by adding facts, but by adding frameworks, by inventing new ways of thinking that make the old ways look incomplete. Webb is giving us the raw material for such reinvention. And somewhere in the data it is collecting, there may be clues to theories we have not yet imagined. Now, as we move toward the conclusion of our journey, through Webb's discoveries, let us return to the image we began with. The little red dots, the strange ancient compact objects scattered across the deep field. The cosmic question marks that started this whole investigation. What are they? We still do not know. But we have learned a lot by asking. We have learned that the early universe was more active than expected, that black holes grew faster than predicted, that galaxies matured sooner than we thought, that chemistry emerged earlier than our models allowed, that dust appeared in places it should not yet be, that the first stars may have been more abundant, more massive, and more influential than we realized, and that dark matter may play a more active role in the cosmos than previously thought possible. The red dots are not just an anomaly. They are a symbol, a visible reminder that the universe has more surprises in store, that our understanding is incomplete, that the work of cosmology is not finished, and that wonder is still alive in the scientific enterprise. And I think that is the most important thing we can take away from all of this. Not any specific theory, not any specific discovery, but the attitude of wonder, the willingness to be surprised, the openness to finding out that the universe is stranger than we thought. That is the attitude that makes Webb worth building. That is the attitude that makes astronomy worth pursuing. And that is the attitude that keeps science alive as a human endeavor. The next time you look up at the night sky, try to remember that most of what is out there is invisible to your eyes. Try to remember that the stars you see are only the closest, brightest, most immediate pinpricks of light. Beyond them, beyond the Milky Way, beyond the local cluster, beyond the local supercluster, the universe stretches out in every direction. And in that vast, vast expanse, Webb is slowly mapping the deepest past. It is showing us what came before, what made us possible, what set the stage for everything we know. It is a gift and it is a responsibility. The gift is the knowledge. The responsibility is to use that knowledge wisely, to hold it with care, to let it change how we see ourselves and our place in the cosmos, to let it humble us when we need humility, and to let it inspire us when we need inspiration. Webb is not finished. The discoveries I have described are just the beginning. The telescope has years of work ahead of it. And in those years, it will show us things that make the little red dots look familiar. It will reveal aspects of the early universe that we cannot yet imagine. It will surprise us again and again. That is the promise of real exploration. It never gives up its secrets all at once. It always has more to show. And when those future discoveries come, we will look back at this moment and marvel at how little we knew, at how much we had yet to learn, at how much the universe had not yet revealed. And we will feel, I hope, grateful. Grateful for the telescope, grateful for the scientists, grateful for the light that traveled so far just to reach us, grateful for the chance to witness the unfolding of the oldest story ever told. Let us sit with that gratitude for a moment, because it is easy to rush through cosmic discoveries, to consume them like any other content. But each one deserves a pause. Each one represents something rare, a moment of contact between human curiosity and the vast silence of the universe. A moment when light and mind met and understanding became possible. Webb is in its own way a monument to that meeting, a tribute to the idea that we can, if we try, understand the universe, that the cosmos is not hidden from us, that it is reachable, at least in fragments, at least in photons, at least in spectra, and that through patient effort and careful thinking, we can piece together even the most distant chapters of its story. The little red dots may be mysteries, but they are mysteries we can investigate, mysteries we can approach with tools and methods and ideas, mysteries that will eventually yield some of their meaning to us. And that is the quiet promise of Webb, the promise that the mystery is not permanent, that the unknown is not eternal, that over time the dark places light up. Perhaps the universe itself is a kind of invitation, an invitation to look, to wonder, to ask. And Webb is helping us accept that invitation more fully than we ever have before. It is showing us the depths we could not see. It is giving us a view we did not have. And it is asking us quietly to bring our attention to the oldest parts of the cosmos and see what we can make of them. As we move toward the end of this long exploration, let us consider one more puzzle that has been sitting quietly in the background, something Webb has observed that has not yet been fully explained. And that is the unusual concentration of galaxies in certain regions of the deep field. In some of Webb's surveys, galaxies are not evenly distributed. They are clumped. They form small groups, tight clusters, and occasional voids where nothing much is present. This is not entirely unexpected. The modern universe is also clumpy with galaxies organized along filaments of the cosmic web. But the early universe was supposed to be smoother. There had not been enough time for gravity to produce the kind of dramatic clumping we see today. And yet, some of Webb's deep fields show clumpy distributions that look more like the modern universe than the smooth early universe we had imagined. It is as if structure was already forming, already organizing, already segregating galaxies into groups in an era when that segregation should have been minimal. This may sound like a minor detail, but it is not. The large-scale distribution of galaxies is one of the most important tests of our cosmological model. If the early universe was more clumped than predicted, it would affect our understanding of dark matter, of inflation, of the initial conditions of the cosmos. It would push back on the idea that the universe began in a nearly perfectly smooth state, and only gradually became lumpy. Now, the observations are still being analyzed. The clumpiness Webb is seeing may not be as extreme as some initial reports suggested. There are ways to reconcile it with the standard model, but the fact that the question is being asked at all tells you something about the direction the field is heading. Webb is forcing us to re-examine assumptions we thought were settled, and that is not a bad thing. That is exactly what we want science to do. We want our instruments to challenge our theories. We want our data to put pressure on our models. We want the universe in all its strangeness to push back against our assumptions, because it is only through that pushback that progress happens. Webb, in that sense, is the ideal scientific instrument. It does not just confirm, it questions. It does not just answer, it complicates. It does not just show us the expected, it reveals the unexpected. And every surprise it produces is another step toward a deeper understanding of how the universe actually works. Let us also briefly discuss something Webb has helped with that does not directly relate to the earliest universe, but which shows how versatile the telescope is. Webb has studied many objects within our own Milky Way. It has observed star-forming regions, protoplanetary disks, dying stars, and even distant exoplanets. In each case, it has provided insights that were not previously accessible. For exoplanets, Webb is especially transformative. It can measure the chemical composition of the atmospheres of planets orbiting other stars. It has detected water, carbon dioxide, methane, and other molecules in these alien atmospheres. It is helping us build a library of what different kinds of planets look like in detail. And in the future, it may detect signs of life itself in the form of biosignatures that could only be produced by biological processes. This capability is not directly related to the early universe discoveries we have been discussing, but it shows just how much Webb is doing. It is not a single-purpose instrument. It is a multi-purpose observatory, or see. And every one of its capabilities contributes to our broader understanding of the cosmos, from the nearest planets to the most distant galaxies. Now, as we approach the conclusion of our journey, let us take one final look at the early universe. Let us step back and imagine what it must have been like. A universe that had just emerged from its own birth. A universe where the first stars were still igniting. A universe where black holes were still forming. A universe where galaxies were still taking shape. A universe where chemistry was still being invented. It was not a quiet place. It was not a peaceful place. It was a place of intense activity, where enormous amounts of energy were being released, where enormous structures were being built, and where the fundamental character of the cosmos was being established. It was a furnace of creation, a crucible of possibility, and out of that crucible over billions of years came everything. The stars, the planets, the elements, the galaxies, the cosmic web, the Milky Way, the sun, the earth, life, us. Every thread of existence, from the smallest atom to the largest galaxy cluster, traces back to that early era. We are all, in a very real sense, products of the early universe. Its chemistry made us. Its physics shaped us. Its history produced us. Webb is showing us our origin, not our species' origin, not our planet's origin, our cosmic origin. The deepest past from which everything we know eventually emerged. And there is something profoundly meaningful about that, whether you think about it scientifically, philosophically, or spiritually. We are looking at where we came from. We are seeing, in some sense, our own cosmic ancestors. And those ancestors, it turns out, were more active, more creative, and more mysterious than we ever knew. The little red dots, the early mature galaxies, the feeding black holes, the hidden stars, the enriched chemistry, the gas streams, the dust, the clumpy distribution. All of these things are part of the story of where we came from. They are part of the long, winding path that led from the Big Bang to this moment, where a single human being is reading about the universe and thinking about its origins. It is a wonderful thing when you let yourself really sit with it. The fact that the universe made itself into something capable of understanding itself. that some of the matter produced in those early eras eventually coalesced into planets, into organisms, into brains, into minds, and that some of those minds are now looking back with telescopes and asking where everything came from. The cosmos, if it could speak, would probably tell us that it is still figuring itself out, that it has been in a continuous process of becoming for 13 billion years, that every age of the universe has its own character, its own challenges, its own kind of beauty, and that we happen to live in an age where we can, for the first time, look back at all the earlier ages and begin to understand them. That is a privilege, not one we earned, just one we happen to have. And what we do with that privilege matters. We can use it to deepen our understanding, to share knowledge with each other, to build a better relationship with the universe we live in, or we can let it slip by unnoticed, undervalued. The choice, as always, is ours. I hope, if nothing else, that learning about Webb's discoveries makes you a little more aware of the universe around you, a little more curious about what is out there, a little more open to the possibility that the cosmos has surprises waiting for us that no one has yet imagined. Because it does. It always does. And every generation of astronomers finds new surprises that were invisible to the generations before. We are lucky to live in a time when those surprises are so plentiful, when a single telescope can transform an entire field in just a few years, when the frontier of discovery is opening up in real time right in front of us. And now, as we prepare to draw this to a close, let us take one more look at the image that started everything. Let us imagine ourselves in front of a Webb deep field, a black background, thousands of galaxies scattered across it, some bright, some dim, some large, some small. Among them, those tiny red dots, those crimson pinpricks that refuse to conform to our models, those quiet invitations to keep looking. And let us remember as we look that each one of those dots is a story written in light, a story billions of years in the making, a story that is still being read slowly by scientists who care enough to spend their lives decoding it, a story that belongs in some small way to all of us, because the universe does not hide its history. It writes it in photons, it inscribes it in spectra, it records it in the motions of galaxies, and if we are patient enough, if we build the right instruments, if we ask the right questions, we can read that history, we can understand it, we can let it change us. Webb is our latest tool for reading the cosmic history, and it is a magnificent one. But it is not the last tool. There will be more, and the reading will go on long after Webb has finished its work. The universe has 13 billion years of material to share with us. We have only just begun the reading. There is something else worth touching on, something that often gets lost in the excitement over individual discoveries, and that is the slow, quiet work of calibration. Every number that comes out of Webb is based on an extraordinarily careful process of measurement. The telescope has to know exactly where it is pointing. It has to account for the motion of its own structure in response to tiny temperature changes. It has to correct for the faint glow of its own instruments. It has to compensate for background noise from the rest of the sky. All of these corrections are applied before the data is considered reliable. And all of that work happens quietly behind the scenes by teams of engineers and scientists who rarely get public recognition. When you see a Webb image, what you are actually seeing is the end result of thousands of hours of calibration. The raw data straight from the telescope does not look like the beautiful pictures you see on the news. It looks like a grid of numbers full of noise, full of artifacts, full of subtle distortions. Turning that raw data into a usable image requires sophisticated software, careful judgment, and a lot of patience. And that is just the imaging. The spectra, which are what allow us to determine redshifts and chemical compositions, require even more careful processing. Every spectral line has to be identified. Every shift has to be measured. Every noise source has to be accounted for. Mistakes are easy to make and they can lead to misleading conclusions. So the teams working on Webb data are painstaking in their approach. They cross-check each other. They run independent analyses. They compare notes. And only when multiple groups agree do they release their findings. This culture of careful verification is part of what makes Webb's discoveries trustworthy. It is also part of why the pace of discovery sometimes seems slow. New images emerge gradually. New papers come out over months and years. The rush of immediate results is tempered by the knowledge that wrong conclusions once published are hard to retract. So the teams take their time. They get it right. And the results when they arrive are usually solid. There have been a few cases where early claims turned out to be wrong. Some redshifts have been revised. Some anomalies have turned out to be artifacts. Some initial interpretations have been replaced by better ones. This is normal in science. It is how the field corrects itself. And rather than being embarrassing, it is a sign that the process is working. Claims are tested. Errors are caught. Understanding improves. Webb is subject to this same process, and it benefits from it. The discoveries we have talked about here, the red dots, the early mature galaxies, the feeding black holes, have all been through multiple rounds of analysis. Many of them have been confirmed independently. Many of them have been refined over time. The picture is not perfect, but it is getting clearer. And this careful work will continue for years. The next generation of Webb results will build on this foundation. And by the time the telescope reaches the end of its operational life, we will have a genuinely transformed understanding of the early universe, not because of any one breakthrough, but because of the cumulative effect of many careful measurements made over many years by many thoughtful people. It is worth honoring that work, not just the flashy discoveries, but the quiet, patient, unglamorous labor that makes those discoveries possible. Every Webb image is a testament to that labor. Every spectrum is a monument to the effort that went into producing it. And the story of the early universe that is slowly emerging from Webb is, in a sense, the collaborative work of hundreds of thousands of hours of human attention. There is another small thought worth adding here, one that connects to the bigger story in a quiet way. It has to do with what a galaxy even is. For most of astronomical history, a galaxy was simply a large collection of stars held together by gravity. That definition worked well for the Milky Way for Andromeda, for the nearby galaxies we could study in detail. But as we look further back in time, the definition starts to get fuzzy. Some of the early objects Webb has found are galaxy-sized in mass, but they do not look like galaxies. They look more like compact clumps. They look like single giant structures. They look like something in between a star and a galaxy, something that resists easy categorization. What do we call these things? Are they galaxies in formation? Are they proto-galaxies? Are they failed galaxies that never spread out? Are they a completely different class of object? The language of astronomy is adjusting to accommodate what Webb is showing us. New terms are being coined, new categories are being proposed, and the old definition of a galaxy is being stretched to include objects that 50 years ago would not have fit the concept at all. This is the nature of science. Definitions evolve as observations improve. The line between a large star and a small galaxy, for example, may not be as sharp as we once thought. In the modern universe, the distinction is clear, but in the early universe, the boundary gets blurry. Webb is helping us see that blurry region, and the vocabulary of cosmology is slowly adjusting to fit. It is a reminder that the universe does not always fit into our tidy categories. It produces objects that cross our definitions. It challenges our taxonomies. It asks us to think more carefully about what we actually mean when we use words like galaxy or star or black hole. And that is a good thing. It keeps us honest. It keeps us humble. It keeps us open to surprise. And this fuzziness of categories applies not just to what Webb is finding now, but to how we think about cosmic structure more broadly. There are supermassive compact objects in the early universe that could be galaxies, or could be enormous single stars, or could be actively feeding black holes surrounded by tight disks of glowing gas. In the modern universe, each of these categories is distinct, well-studied, and easy to identify. But in the early universe, they seem to blur together. They share features. They occupy similar regions of parameter space. They produce light that looks at first glance very similar. This blurring is itself an interesting clue. It suggests that the categories we use today may be the result of billions of years of cosmic sorting. Over time, objects settle into clear types. Galaxies become galaxies. Stars become stars. Black holes become black holes. But in the beginning, before that sorting had taken place, the universe produced a continuum of structures that did not yet know what they were supposed to be. Webb is showing us that continuum. It is showing us a universe that was in its youth less differentiated than it is now. And from that youthful blended state, the familiar cosmic order gradually emerged. It is a different way of thinking about cosmic history, not as a smooth path from simple to complex, but as a process of sorting, separating, and defining. For a long time, astronomers spoke of the edge of the observable universe, the furthest point we could see, the boundary beyond which light had not had time to reach us. That edge moves as time passes, and as more light arrives from ever farther away. But the concept of an edge has always been an important anchor in cosmological thinking. It defined the limit of what we could know. Webb is in a sense testing that edge. It is pushing against it. It is getting closer to it than any telescope before. And in doing so, it is showing us that the region near the edge is more populated, more interesting, more structured than we had assumed. The edge is not empty. It is full. This realization changes how we think about the observable universe. It is not a sphere with clear borders. It is a rich, layered, textured environment that stretches as far as we can tell, all the way to the limits of our vision. And beyond those limits, there is probably more, much more. Regions of space that we cannot see because the light from them has not yet arrived. Regions that for all practical purposes are invisible to us forever. Unless the universe somehow changes its fundamental laws, we will never have direct access to those regions. They are outside our cosmic horizon. But even the region we can see is enormous, and Webb is making it feel even more enormous by revealing how much is happening in every corner of it. Every deep field is packed with galaxies. Every spectral line tells its own story. Every redshift places an object in a particular moment of cosmic history. And the overall effect is a sense of richness, of plenitude of a universe that is full to the brim with meaning for those willing to look. That is a good thought to carry with us. The universe is full. Even where it looks empty, it is full. Even in the darkest regions of the deep field, there are objects, there are processes, there are stories. Nothing is truly empty, at least not in the cosmic sense. The void is populated, the silence is alive, and our relationship with that universe is one of steadily deepening familiarity. Each generation of astronomers knows more than the last. Each instrument reveals layers that were invisible to its predecessors. Each discovery prepares us to ask better questions next time. The relationship is not static, it is growing. And it will keep growing as long as there are minds willing to engage with it. Webb is in its own way just the latest chapter in that relationship. It is a particularly important chapter because it is giving us access to the oldest parts of the universe we have ever been able to study in detail. But it is not the final chapter. There will be more chapters, many more, and the story will continue for as long as humanity continues to look up, continues to wonder, continues to ask. For now, we have the discoveries at hand, the red dots, the early mature galaxies, the supermassive black holes, the chemical enrichment, the gas streams, the hidden dust, the clumpy distribution, the anomalies, the surprises, the questions. All of it is ours to contemplate. All of it is ours to wonder about. All of it is ours to carry with us as we go about our ordinary lives, feeling a little more connected to the cosmos than we did before. So what have we learned from all of this? What is the takeaway from Webb's first few years? The universe is older than our stories, for it have been sophisticated. It contains more variety than our models have captured. It produces objects that do not fit our expectations. It builds structures faster than we predicted. It runs processes that we do not fully understand, and it invites us always to look more closely. We have also learned that astronomy is not just about distant objects. It is about humanity. It is about what we can do when we work together across borders, across decades, across disciplines. Webb took thousands of people to build. It took international cooperation on a scale that is rare in other fields. It took dedication that spanned entire careers, and the results are shared freely with the world. That is something to celebrate. In a world often marked by division and conflict, astronomy reminds us that we can, when we choose to look beyond our differences and pursue knowledge together. We have learned too that the unknown is not something to fear. It is something to approach. Every Webb discovery begins as a question. Every spectrum begins as a puzzle. Every image begins as an invitation to investigate further. And by leaning into the unknown, by refusing to pretend we have all the answers, we keep the field of science alive. We keep it honest, we keep it curious, and we have learned that beauty and truth are not opposed. The more deeply we understand the universe, the more beautiful it becomes. The little red dots are beautiful, not in spite of being mysterious, but because they are mysterious. The early black holes are beautiful because they are strange. The mature early galaxies are beautiful because they defy our expectations. Every unexplained observation is an opportunity for awe. Every anomaly is an invitation to wonder. I hope as you have listened to this story unfold, you have felt a little of that wonder yourself. Not the anxious wonder that comes from not knowing what is going on, but the settled, patient wonder that comes from being in the presence of something larger than ourselves, something older, something more enduring, something that will continue long after any of us are here to witness it. The early universe made us. The discoveries of its strange structures remind us of where we came from, and the ongoing work of Webb and all the telescopes that will follow it promises to keep revealing that origin in deeper and deeper detail. Perhaps one day we will understand the little red dots completely. We will know what they were. We will know how they formed. We will know what role they played in the grand story of the cosmos. And when that day comes, we will look back at this era of mystery with fondness. We will remember it as the time when the universe first began to show us its hidden youth, when the golden mirrors of Webb captured light that no one had seen before and used it to open a window onto the deepest past. And we will tell that story too whoever comes next, to the children, to the students, to the astronomers who have not yet been born. We will tell them about the time when Webb launched and when it started sending back images, and when those images contained surprises that forced us to rethink the foundations of cosmology. And they will listen, and they will ask questions of their own, and they will build new instruments to answer them. The cycle will continue. The exploration will never truly end. That is, in a way, the most beautiful thing about what Webb is showing us. Not just the specific discoveries, not just the mysteries, but the reminder that the universe is inexhaustible. It will always have more to give. There will always be another question, another anomaly, another puzzle to investigate. And humanity, curious by nature, will always rise to meet those puzzles with new tools and new ideas. So when you next go outside on a clear night and look up at the stars, try to remember that you are looking at just a fraction of what is actually there. That beyond what your eyes can see, there are galaxies. Beyond those galaxies, there are more galaxies. Beyond those, there are the faint traces of the first stars. Beyond those, there are objects that Webb has been studying. Objects that have been sending their light toward us for billions of years. Objects that were doing their mysterious work before our sun even existed. And among them, in all likelihood, are the little red dots, quiet, ancient, waiting, still carrying the secrets of the early universe in their compact crimson glow, still posing questions we do not yet know how to answer, still inviting us to look closer, to think harder, to remain curious. The universe is full of such invitations, and Webb is helping us accept more of them than ever before. May we keep accepting them. May we keep building tools that can reach further. May we keep asking questions that matter. And may we keep finding that the cosmos, for all its strangeness, for all its scale, for all its deep time, is a place where we belong, a place that made us, a place that is still making itself, a place worth knowing. That is what James Webb saw beyond the stars. Not just objects, not just data, but a reminder of who we are and where we came from, and a gentle, persistent invitation to keep looking, keep wondering, keep dreaming about what else might be out there waiting patiently in the silent dark for the next curious mind to ask the right question. Thank you for spending this time with me. May your sleep tonight be deep, and may your dreams drift out among the stars. Until next time.